All right, come on. Oops, that's not what I wanted. There we go. All right, we'll see how this works. Okay, so where we are headed today then is we're going to start chapter 7. We've got basically 2 chapters left for the most part, and then we might have a little bit more time at the end of the year. We'll kind of see where we're at. But chapter 7 is the kind of the next progression. We're going to look at what are called exponential functions, which I think you learned a little bit about way back in Algebra 1, but not, I don't think you went too far at all into this. And then we're going to get into what are called logarithmic functions as well, this chapter, which part of the reason the week before break we talked about inverse functions is logarithms are inverses of exponential functions. Okay, just like taking the square root was the inverse of squaring something. Taking the cubed root was the inverse of cubing something. That's where we're headed. That's what we're going to take a look at for this one. So first thing we're going to take a look at here is this. Okay, we're going to kind of look at 3 main types of functions, and as we work our way through it, just kind of how can you identify when you have each different type of function. So if we take a look, let's go to the next page here. And if we take a look, first we're going to look at our linear functions. Okay. And this is just some basic linear function. This is the function y equals x, is what this is. But I'm going to put some points on here. And we're going to, you notice, we're going to take a look at the pattern here. So here's some actual kind of nice points that are on the line. And if I pick off some of those points, what I'm going to have you take a look at is, so one of the points that's on this line is -1, -1. Another point on the line, 0, 0, 1, 1, 2, 2, okay, so on and so forth. And I'm not so worried about, and it doesn't necessarily have to be the same numbers, okay? For this line, it does because it's y equals x, but you could have any equation. It could be y equals 3x, y equals 4x, y equals -1/2 x. But what I want you to take a look at is, as the x coordinates go up by 1, what I want you to look at is what's the pattern of the y coordinates. Okay, what's happening to y as x goes up by 1. So if you notice, from this y coordinate to that y coordinate, we're adding 1. Then from here to here, we're adding 1. Here to here, we're adding 1. Okay, that addition, what we are adding is actually the slope of this line. Okay, so if I was adding 2 every time, we would have a slope of 2. Okay, if I was adding 2/3 every time, we would have a slope of 2/3 for that line. Okay, and so this pattern, what I want you to notice with linear functions, it's got that constant addition or subtraction. Okay, because it could go down as well. You can have a negative slope, but what we're looking for with linear functions is we've got that repeated addition, right, or repeated subtraction, if you want to think of it that way as well. Right, either one of those. So that's how you can identify that constant amount. We can't add 1 and then add 2 and then add 5. Okay, then that would not be linear. You got to add the same thing every time. Okay, so that's the first one. Let's go to the next one. Let's take a look at quadratic functions. So if you look at quadratic functions, this is the graph of y equals x squared. Okay, let me pick some points and let's take a look at the pattern that we have here. So here's a point here. Just going to pick off the nice ones basically that I'm noticing. So there's a whole bunch of different nice points on there. Again, just like any other parabola, it always has that U shape. It's always got the symmetry. Okay, so that's why this point here, these 2 points kind of match up. Those 2 points match up. The top 2 points match up. Okay, and so if I start taking a look, I'm going to start with the origin. So let's say we go 0, 0 as my first point. Then the next point is 1, 1. Then we go to 2, 4. And then we go to 3, 9. And we could keep going. But again, what I want you to look at is what's happening to the y values. As x goes up by 1, what's happening to y? Okay? When it was linear, we added the same amount every time. It was a constant thing that we were adding. This time, if you notice, we add 1. Then all of a sudden now we're adding 3. Then we're adding 5. Okay, and so on and so on. So notice, first off, we're not adding the same thing, which is why it's not linear. Okay, the slope, if you will, is changing. Between the first two, we kind of have a slope of 1. Between the next two, we have a slope of 3, that rate of change. Okay, and so because the slope is changing, that's what makes it into a curve. And what I really want you to notice on this one is quadratic functions have that where you're going up, where you're adding the next odd number every time. Okay, add 1, add 3, add 5. The next one, if we just continued the pattern, I would add 7. Okay, and my next coordinate, I would have the point 4 comma 16, which would then, like I said, I'd be adding 7 to that next one, and so on and so on and so on. Okay, so you can identify quadratic functions by going through and looking for that odd number pattern. Okay, that's what you're taking a look at. Any questions so far on the difference between linear versus quadratic patterns? Linear has that constant amount, that constant slope. Quadratic has those odd numbers is what you're looking at. Basically, what that then leads us into, we've looked at those two before. Here's an example of an exponential function. Here's an example of an exponential function. And in this case, this is what's called exponential growth, which we'll get into later on. But now if we take a look at some of the nice points that are on here, here's one here, here's another one, there's another one there, here's another point there. So there's 4 points right there that are nice points on the actual graph of this exponential function. Okay, if we put the coordinates down, first one we have is 0, 1. Then we're at 1, 2. Then we're at 2, 4. And the last one that I picked was 3, 8. So this time, when you look at the y values, what's the pattern? What's going on here? You get from one y value to the next. How are the y values growing? Yeah, times 2. It's got that common multiplier. Okay, so in this case, it's times 2, times 2, times 2. Okay, is the idea. And that's the part I'm going to add a little note here. That's what you're looking for when you have, that's what makes something an exponential function, is that repeated multiplication. It's got that common multiplier. Okay, so I'm going to just put that in here. And we have a common multiplier. Common multiplier. That's what an exponential function is. Times 2, times 2, times 2, times a third, times 5, times whatever the number is. It doesn't matter what we're multiplying by necessarily, but it's got that repeated multiplication, and that is why you end up with this curve. That's why things grow so fast, because you're taking what you had before and you're multiplying it by something, so it gets much bigger very quickly. Then you take that and multiply it by that same number again, and it gets even bigger and even bigger and even bigger. This, ideally, if we even start right away on day one on kind of relating this to real world type stuff, this is ideally how you would like your money. If you put your money into like a bank account or something, you would love your money to grow like that. Okay. Where on day one, maybe you've got $1. Day later, you got $2. Day later, you got $4. Then you got 8. Next day, you got 16. Before you know it, you're sitting with thousands and thousands of dollars because of that exponential growth. Okay. Now, that's not real realistic, but that's what you would love to have happen. That's what you're looking for. Okay. So here's what I want you to do. On the next part, the quick check. Take a look at those data tables, and I want you to tell me one of them is linear, one of them is quadratic, and one is exponential. I want you to take a look at the patterns of the y values and tell me which one's which. Just circle it at the bottom. Which one of those tables represents a linear function? Which one represents quadratic? And which one is exponential? All right, so let's take a look. What about the first one? What kind of equation do we have? What kind of growth do we have here? Linear, quadratic, or exponential on the first table? What'd you come up with? Linear? Okay, why linear? Logan. Yeah, you take a look at the pattern on what's going on here. Subtract 3, subtract 3, subtract 3, and there's that constant amount. It's staying the same every single time. It's that repeated, in this case, subtraction. So that is what makes this linear in this case. Matter of fact, if you were to graph those points, that would be the slope of your line. It would be -3. Okay, so it's decreasing by a value of 3 every time. So that makes that one linear. How about the next one? How about the middle one? So we got our linear one. Is the middle one quadratic or exponential? What do you think?
Exponential.
And why do you say that, Bella?
Well, I looked at the sheet and I did that, but because this goes up by like the power of 3.
Yep. And so, and that's what we're looking for, is we're looking for that repeated multiplication to see if it's exponential. It's a little bit difficult on the first ones just because they're fractions to notice it. So once you get down to the second part, it's a little bit easier to notice here that here we're multiplying by 3, multiply by 3, multiply by 3. It is this, and that's what you're doing at the top too. You're just not as familiar, you're not as used to dealing with fractions. So 1/27 times 3 is 1/9. 1/9 times 3 is 1/3. And because of that repeated multiplication, that is an exponential function. Right? That's what makes it exponential. That's your multiplier. And therefore, kind of by default, then the last one has to be the quadratic one. But if we talk about why it's quadratic, if we look at the pattern, notice from 13 to 8, we're subtracting 5. Then we're subtracting 3. Then we're subtracting 1. There's those odd numbers I was talking about. There's that odd number pattern where we're not adding or subtracting the same thing, so it's not linear. We're not multiplying by the same thing, so it's not exponential. The odd numbers makes it quadratic. Okay, yeah, Bill.
So if it's odd numbers only, it's quadratic, but if it's an even number, then it's not.
Yeah. What you'll see is you'll see odd numbers. Correct. Yeah, you'll be looking for the 1, 3, 5. Okay. So the first thing I wanted you to understand today, as we get into this chapter, is what's the difference between things that are linear versus things that are quadratic versus things that are exponential? How do I identify it? And this common multiplier is one of the main features of an exponential function. Okay. All right. So if we keep going, then here is your definition of an exponential function. Here's where we're now going to get into a little bit more specific to exponential. Okay. So if you take a look, and I'm going to kind of just highlight a few things here. There's our first part right there. There's our general equation of an exponential function. Y equals A times B raised to the X power. Okay. A times B to the X power. Where B is a positive number other than 1. So you're starting off your B value, by the way, that's your multiplier. That's what because it's raised to the X power, they're saying you're multiplying it X number of times over and over and over again. And so I'll add that in here real quick as well. This is your multiplier. Okay, the B value is your repeated multiplication, is what you're taking a look at. So that number is going to be something other than something positive, other than 1. Okay, and then A is what's called your initial value. You got to kind of have a starting point with exponential functions. If something is going to either grow or decay exponentially, you have to start with something. Okay, and that's where A comes into play. A is that initial value. How much am I starting with? One of the applications next week, we'll kind of talk about applications of exponential functions. One of the most common ones is population. As populations of cities or animals or whatever it is, as populations grow, a lot of times they grow exponentially. Well, obviously, in order for a population to grow, you got to start with something. Okay, that's where that A value comes into play, that initial value. Okay. One thing I want you to notice: how do you recognize whether something is an exponential function? Let's say I did not give you an actual table, okay, like we were doing before. And then how do you know if it's exponential? It's right here. Note, the variable is now in the exponent. Anytime there's a variable, if your x is in the exponent, that is an exponential function. Okay. So it's not because you have an exponent. It's when there's a variable in the exponent, okay, that you're solving for. And so what I mean by that is, x squared, for example, x cubed, those are not exponential functions. X squared is a quadratic, x cubed is a cubic, okay? Exponential functions have that variable up in the exponent, is what's going on with that. Okay? Does anybody have any questions about that at all? All right, so there's some of the basics. We're going to come back to this a little bit later on anyway, but we'll get to that. So then if we go through, so one of the properties that we have not yet talked about in any other type of equation or graph or anything, one of the properties of an exponential function is they have something that is called an asymptote. Okay, and an asymptote, you can see by the definition, is a line that a graph approaches as you move away from the origin. Okay, keyword there is approaches. It will never actually quite get there. It just keeps getting closer and closer and closer, but never quite gets there. Okay. Here's the example that I gave to some of the other classes. I'm kind of an idea what an asymptote is. So if you ever watch football, play football, any of those kind of things, in football, there's a penalty. There's a half the distance to the goal penalty. Okay. So let's say you've got the ball. You're on your football team. You've got the ball. You're on your own 10-yard line. You commit a penalty. And they say, all right, half the distance to the goal. So they move you back to the 5. Then you commit another penalty. Half the distance to the goal. They move you back to the 2.5-yard line. Commit another penalty. Now they move you back to the 1.25-yard line. The question I have for you is, will you ever actually end up in the end zone? No. That's the whole point of that penalty. Is it keeps moving you back. There's still a penalty every single time, but you're never actually going to quite get to the end zone. You're still going to be in the field of play. That's what an asymptote is. It's the exact same idea. You're never going to actually quite get to the asymptote. You're just going to be, it's going to get really, 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 really close. Okay. So for example, if you take a look. So if you take a look, all of these graphs have at least one asymptote. The first 3 here are actually types of exponential functions. So this first one, we've got exponential growth. Here's where your asymptote is, right here. I'm just going to kind of draw it in as a dotted line. I have an asymptote, a horizontal one at y equals -2 on that first graph. Okay. And as we're talking about, if you think about this as like your goal line, if you will, here's the idea that the graph is approaching. It's going to get really, really, we're moving away from the origin. It's going to get really, really, really close to y equals -2, but it's never going to quite get there. We might be at -1.999. Then the next point, we might be at -1.999. Then we might be at -1.9999, and so on and so on. But we're never going to quite get to -2. Okay. If you take a look at the next one, same idea. The only difference is our asymptote here is at y equals 0. At y equals 0, we have that horizontal asymptote. So it kind of just shifted basically we took this graph and kind of shifted it up 2 spots. If we take a look at the next one, this is basically an exponential function that then now has been reflected. And therefore, instead of increasing really quickly, now it's kind of going through and it's decreasing. Okay. So it's a reflection of an exponential function. And again, if we take a look, we have a horizontal asymptote right up here. And what is that? 1, 2, 3, y equals 3. So that graph, as x is going to -infinity, the graph is approaching 3, but it's never going to quite actually get there. Never touches or crosses an asymptote. Okay? It never touches or crosses. Now, the last one, this is actually the last chapter. These are the graphs of the last chapter we're going to do when we get into chapter 8. That one actually has 2 asymptotes. One horizontal and one vertical. Where's the horizontal asymptote? At y equals what? 1. Yep. If you take a look, y equals 1. Here's your horizontal one right here. At y equals 1, there's a horizontal asymptote. That's kind of why the curve is bending in both of those directions. Where do I have a vertical asymptote? At x equals what? What value of x? Wait, what is it? It's not one. It's negative one. There you go. It's right here. Right there is your, at x equals negative one, you have a vertical asymptote. Okay, so it's kind of like, those are almost like boundary lines, if you will, where it's sandwiching the two curves in between those boundary lines where it can't cross those, but it's getting really, really close to both of them. Okay, so that one, that's an example, like I said, from the next chapter, but I wanted you to see one that had multiple ideas. Okay, so some properties, like I said, if I go back for a second, the equation, again, is here. General equation, some properties, that multiplier idea, and one of the properties of the graph, you will always see some sort of asymptote, okay? And it's almost always going to be a horizontal asymptote with exponential functions. Okay? Any questions so far? We're doing okay? All right, let's keep going. So now, if we go to the other sheet that I handed out to you, now we're going to get into kind of the specifics of graphing exponential function. And so if you notice here, example number 1 says the function y equals 3 to the x. That is called, move this down so I can write on it. That is called an exponential function. Because the exponent, okay, the power, is a variable. That's what's going in this blank right here. Anytime your power has a variable, anytime the exponent has a variable in it, that makes it an exponential function. Okay? So y equals 3 to the x is an exponential function because the x is the power. All right, so if we actually take a look, for your first few here, we're going to take a look and actually evaluate some things. We're just going to plug some numbers in. Okay, so if you notice what they did on the first one, they took -3 and they plugged it in for x. They put it in as the exponent and then got an answer from there. And now here's where the chapter 6 stuff comes into play. Okay, here's where some of that stuff that we talked about in the last chapter comes in. So 3 to the -3rd, remember a negative exponent does not make a number negative. It turns it into a fraction. Okay? So 3 to the -3rd is 1 over 3 to the +3rd. 3 to the 3rd power is 27. So the x value that got plugged in was -3. The y value that came out is 127. And therefore, the first point that I have on my graph is -3, 127. I could go through and I could at least approximately plot that on the graph. Let me stop for a second. Does it make sense where the 127th is coming from? How they got the 127? Like I said, -3 goes in for the power. Negative exponent turns it into a fraction, and then evaluate from there. If we do another one, same idea for -2, if I plug that in, that would give me 3 to the -2nd power, which is the same thing as 1 over 3 to the +2nd power. And 1 over 3 squared is 1/9. So I plugged in -2 for x. I got 1/9 back out as an answer for y. So another one. If I plug -1 in, 3 to the -1st power is 1 over 3 to the +1st. And 1 over 3 to the +1st, that's just 1/3. So I plugged in -1, I got 1/3 as an answer. What happens when I plug in 0? What's 3 to the 0 power?
Or 1.
1, there you go. Remember, anything to the 0 power is 1. So when I plugged in 0, we got 1 as an answer. So there's my y-intercept on that one. And now it gets a lot easier because now you're just plugging in whole numbers. 3 to the 1st power gives you 3. So you plugged in 1, we got 3. 3 to the 2nd power gives you 9. Plugged in 2, we got 9 as an answer. And 3 to the 3rd power is 27. When I plugged in 3, I got 27. So quick question. I'm going to go all the way back to kind of where we started. What's the pattern of the y values? We take a look here. How are they growing? What's the pattern going on here? Well, that's what we got. Yeah, if you take a look, Well, this actually is one of the ones that we looked at. 1/27, 1/9, 1/3. We're multiplying by 3 every time, which hopefully makes sense. Because remember, I told you your B value, the base that we have, that is your multiplier. That 3, whatever that is, the base is of our exponential function, that's that repeated multiplication. So it hopefully shouldn't surprise you too much. It's times 3 times 3 times 3. That's what's going on. So if we take a look at the graph here, here's what we have. -3, 1/27, that's basically 0. We'll put that on there. -2, 1/9, that's still basically 0. We'll put that on there. 1/3, we're getting a little bit bigger now. 0, 1, now it's starting to grow. 1/3, now it's starting to grow even faster. 2, 9, and then 3, we would be up at 27, and all of a sudden it grows really, really, really fast. Okay. And if we go through and we kind of sketch this in, there's what your graph looks like for y equals 3 to the x power. Again, it would be really, really nice if your money would grow like this. You had some money and all of a sudden went from $9, next day you had 27. If we did it again, the next day you'd have 81. Day after that, you'd have 243. And all of a sudden you got a lot of money really, really, really quickly. Couple of things. Again, let me go back to real life type of examples. Okay. Anybody tell me this could not come at a more perfect time? And it actually worked out this way last year too. Anybody tell me something in real life that grows exponentially that we've been experiencing in the last year? There's COVID cases right there. That is exactly when they talked at the very beginning about flattening the curve. You've ever heard that? You heard that term at the very beginning where you're talking about we need to flatten the curve. Here's the curve right here. This is the curve they were talking about. It was going so fast and it was growing exponentially that in this case, they were trying to get that to turn around. So it is growing exponentially in this case. That is a good example of what happened with the COVID cases. If you followed the trend and you actually plotted the data of number of positive cases, it looked a whole lot like that. Okay. And now at least hopefully we're back down and going the other direction. There's another one. Everybody ever seen the movie Pay It Forward? Ever seen the movie Pay It Forward before? I was gonna say the movie Pay It Forward, if you've ever seen it, basically a little kid comes up with an idea, a classroom idea for, I don't know whether he's in middle school or high school or I don't know what he's in, but he comes up with an idea to go through and he's going to go through and help 3 people with something. And then the job of each one of those 3 people is to help 3 people. And then every person then is supposed to pay it forward and continually helping. And it actually turns out that it's this exact function. That's why I bring this up. This is how fast people could be helping people. If it started with 1 person, okay, there's the 1 person right there. Okay, there's our initial value. And that person helps 3 people. And then each one of those helps 3 people. Now there's 9. Each one of those people helps 3 people. Now there's 27. And it just grows very, very, very quickly. So if you've ever seen the movie Pay It Forward, it's dealing with that concept of exponential growth and how quickly things can be affected. All right, so if we take a look, by the way, where's the asymptote on this one for this graph? If I were to draw this in, where would the horizontal asymptote be? Yeah, that would be a y equals 0 here. I put that in, and I'm going to go ahead and actually put it in. So we do have a horizontal asymptote at y equals 0. Okay. We said, remember back to the definition, we said that it has to be a positive number, okay, which is kind of why that horizontal asymptote is there. All right, so now, if we take a look, let's kind of fill in some of the blanks here. We've talked about them, but let's fill some stuff in. Since the y values increase as the x values increase in the example above, this is what we just noticed is what is called exponential growth. What we just noticed, what we just talked about is we talked about COVID cases, we talked about Pay It Forward, all that kind of stuff. That is how fast something can grow exponentially. The question then is, in the exponential function, the y values can never be less than, we kind of just talked about it. We've got that horizontal asymptote, can never be less than 0. Okay? Can never be less than 0 in this problem. Or even equal to 0 for that matter. And therefore, that leads right into the next line. Since the y values never equal 0 in this function, there is a horizontal asymptote at y equals 0. All right, and then the last concept that we need to take a look at before we go into the next idea. The last concept that we need to take a look at is domain and range. Well, in this case, when we think about domain, remember before break, we talked about restricted domains and things along those lines a little bit. Okay. If you think about the equation that we have here, is there any number that you are not allowed to raise 3 to?
0?
What's 3 to the 0 power?
Yeah.
So that works, right? I think, is there any restriction on this? Your instincts are right, by the way. Okay? Your instincts, I saw multiple people right away be like, no, I don't think so. And you're right. The instincts are right on that one. There is nothing. We can raise 3 to any power I want. Positive numbers, negative numbers. Matter of fact, we did it up here. With positive numbers, 0, negative numbers. We could put fractions in. We did it in the last chapter. We talked about fractions and how you do fractional exponents. And so what I'm getting at is the domain is all real numbers. Okay? There are no restrictions on the domain. I can plug anything I want in for x. How about my range? What about my y values? We kind of talked about that. Y value, yeah, try that again. The y values have to be greater than what? 0. The asymptote. Wherever the asymptote is, that's where the y values have to be greater than in this case. Okay, so we've got y equals 0. Therefore, our range is y has to be greater than 0. All of the y values of our exponential function have to be above that graph. Okay. All right, let's go to the next one. Let's take a look. The difference now is instead of going from 3 to the x, now we're going to take a look at 1/3 to the x power. Okay, now we're going to look at 1/3 to raise to the x power. So a couple of quick things mathematically as we plug this in. If I plug -3 in, we would have 1/3 raised to the -3rd power. Okay, we're plugging in -3 for the exponent. Well, when it's raised to the -3rd power, we can go through and we could change it into a fraction 1 over that. What ends up happening, the easiest way to make this work is whenever you have a fraction raised to a negative power, you can just take the reciprocal of the fraction. So therefore, 1/3 to the -3 is the same thing as 3/1 to the +3rd power. Okay? 3/1 to the +3rd. If you take the reciprocal, that negative exponent will go away. And now 3 to the 3rd power is 27. So when I plugged in -3, I got 27 as an answer. Same idea for the next one. If I take 1/3 and raise it to the -2nd power, that's the same thing as 3/1 to the +2nd power. And 3 squared gives you 9. We'll do one more and then we'll see what the pattern is from here. 1/3 to the -1st power is the same thing as 3/1 to the +1st power. And 3/1 gives you 3. What's the pattern of the y values? What's happening? What's my multiplier? Where it's not 3. 1/3. 1/3. You know, which again, hopefully is not super shocking to you. The base of the exponent here is 1/3. Notice 1/3 of 27 is 9. 1/3 of 9 is 3. What's 1/3 of 3? 1. There's our next answer. 1/3 of that would be 1/3. 1/3 of that is 1/9. And then you get 1/27. So we've got all these points. 0, 1. 1, 1/3. 2, 1/9. And so all I did there is I kind of skipped the plugging it in and just used the pattern to fill out the rest of it instead of plugging in every single value to get an answer. Now, if we take a look at the graph, we are at -2, 9. Negative 1, 3. Now we're decreasing. 0, 1. On the third, and it just keeps getting closer. So it looks something like. Something like that. Where's my horizontal asymptote on this one? Y equals what? Still at y equals 0. Yep. What's the only difference between this graph and the last one? Yeah, instead of exponential growth, right down below there where it says definition 3, this is what's known as exponential decay. Exponential decay. But instead of something growing very, very rapidly, this is an example of something that's decaying, something that's decreasing really, really rapidly. Okay. We already talked about the question, is there an asymptote? Yes, there is. It's at y equals 0. Okay. So it's approaching 0. And then by looking at the graph above again, what's the domain? That one's all real numbers again. I can take 1/3 and raise it to any power I want. What's the range? What's the range? Well, it has to be greater than 0 again. That's where that asymptote comes into play. Okay. So the range is y is greater than 0.
What if y is greater or equal to 0?
No, because what happens is as this graph approaches 0, it doesn't actually get there. It's that goal line idea. The football's never going to actually be on the goal line. It's just going to keep getting closer and closer and closer. Same thing with this graph. It's never going to actually get there. It's just going to get really, really close. That's why it's not equal to. Okay. So now here's my last question, then we'll kind of wrap up the lesson here. Last question. What do you think the difference is between exponential growth versus decay? Like here we had 1/3 to the x, that was decay. Here we had 3 to the x, that was growth. What number do you think? Remember, it's a multiplier. What do you think the key number is? You have the right idea, but it's not necessarily because it's a fraction. Take a look back at your definition. Right?
1.
1 is the key idea. 1 is the cutoff. Anything bigger than 1, let's say you start with something and you multiply by a number bigger than 1. Isn't it going to get bigger? Going to grow? Multiply by 2, things are going to get bigger and bigger and bigger. What if you multiply by a positive number? So it's got to be bigger than 0, but less than 1. A third. You're going to get smaller and smaller and smaller, or a half, or 2/3. Okay? So any number, so 1 is basically that cutoff. Any number where our multiplier is bigger than 1 is exponential growth. Any number between 0 and 1 is going to be exponential decay. Okay? So if we go back and we apply that then to the sheet that we were taking a look at. So take a look at problem number 5 then. Exponential growth or decay just by looking at the graph or looking at the equation. That one's going to be decay because your base, the 1/4 is your multiplier, which means things are going to get smaller every time. So this, I'm just going to put a D next to it for decay. How about number 6, growth or decay? That's growth. We're doubling things every time. How about number 7? It's not decay. Kind of a trick question. What happens if I multiply by 1 over and over and over again? Nothing. So therefore, this would be neither. This is not exponential growth or decay. That's why it's not allowed to equal 1 as part of the definition. That was why in that definition where it had to be a positive value, but not 1. Because if it's 1, it doesn't change. How about number 8? Growth or decay? That one's growth. How about number 9? Neither. That one's going to be neither again as well. Because 0 raised to any power is also going to be 0. It's not going to change. So that one would be neither. And how about the last one? That one is decay. So whole point of today's lesson was to get you the idea of what is an exponential function, what does it look like, and what I want you to do then is, like I said, I'm going to have you graph. I'm going to give you a worksheet that's just based similar to what we just did, where you're graphing exponential functions. Matter of fact, let me actually bring it up just for a second, because I've had a couple of people from yesterday that turned this in. What I want you to notice, this will be. Let me hand it out and then I'll talk about it quick, so that you can see what I'm referring to. So this This whole thing is your assignment. Okay, this is due by Thursday. So if you take a look, one of the things that, like I said, that people have gotten confused by, I've had two people turn this in and turn it in incorrectly. If you look at the first page, notice how it says graphing exponential functions practice is very, very similar to what we were just doing. Then you go to the next page on the backside and same thing. Okay, it's got the same idea. It's very similar to what we just did. Well, then a lot of people are stopping there and turning it in. Okay. Because now it says worksheet number 2. This is still part of the whole packet is your assignment. Okay. And I know it looks like it's a lot of problems. It's not. There's only like 6 or 7 problems or something like that total in here in terms of graphing problems. So the whole packet, ignore the fact that that says worksheet number 2. This whole thing is your first assignment. Okay. Reminder, tomorrow when you come in, you can pick your seats, pick where you want to sit, pick who you want to sit by, and we'll go from there. Have a good day. Welcome back. Yep. Have a good one, Bob. Yes. No, don't worry about it.
Okay.